Roberts. Sorry, I have to correct myself. Dr. Toby Roberts.
No problem. I'm just getting this going. So it's good evening for me in the UK. It's a great honour to be addressing you all this evening. London is where I learned my trade, and in the next hour I'm going to walk you through my 30-year journey getting to grips with the dewatering for several major infrastructure projects in London. I'll start by looking at the hydro-geological setting that we have, and then I'm going to use a series of case studies to illustrate the range of innovative groundwater control techniques that we've developed to tackle these projects. So that first photograph is one of the main drive shafts for the Crossrail project. The tunnels are finished. It's going to be a new part of the London Underground system called the Elizabeth Line, due to open in about a year's time, and it'll feature in a couple of the case studies. So let's have a look at the setting. It's divided into three sections, the setting. First of all, the geotechnical profile. This has been well known since Victorian times. London sits in a basin with the chalk at the bottom and a succession of soils above, which hopefully you'll get to know in the course of the next hour. The early tunnels that the Victorians constructed were either cut and cover, or they were constructed in the London clay, which is perfect material for tunnelling. Brunel actually made the mistake of constructing his first tunnel under the Thames too far to the east, and he finished up in the Lambeth group and ran into significant problems, although he did finally succeed. His tunnel still remains part of the London Underground network. The chalk does gradually rise to the east, and the whole profile rises to the east with the superficial soils eroded away. Hydrogeologically, or the hydrogeology, is relatively complicated, and I'm going to look at that in a little bit more detail. We have at least 3 aquifers, and we have different water levels in the aquifers, and we'll look at the reasons for that in a moment. The chalk is a major aquifer, major water supply aquifer in the UK. In London, it's recharged to the north and the south, but not in central London because the clay acts as a barrier boundary, the London clay. What's gradually happened in London is that each time someone builds a tunnel, when they want to build a new tunnel, it finishes up being deeper. And the tunnels have got deeper and deeper and deeper. And now the newer tunnels, and all the ones I'm talking about, are either in the bottom of the London clay or getting into the Lambeth group, the Thanet sand and the chalk. Part of the reason why London has such a good underground system is because of the London clay, because that was such an easy material to tunnel through. So look at the geotechnical setting in a little bit more detail. Made ground and alluvium at the top. Then we have the river terrace deposits. Those are known as the upper aquifer, and there's plenty of dewatering goes on in that, but I'm not going to talk about that in the course of this presentation. The London clay, up to 70 meters thick. It's impermeable, it's a hydraulic barrier. It's a stiff, fissured, heavily over-consolidated clay. London had more than 1,000 meters of ice on it, which is why the ground is so stiff and consolidated. The Lambeth group we'll be hearing quite a bit about. It's typically 12 meters thick, and it's mostly clay. However, it has sand laminations and they increase in places up to channels. So they vary between sort of 2 and 30 meters wide and of uncertain length, but the length may be hundreds of meters or kilometers. And the thickness varies from just a few millimeters to 12 meters. And that's termed the intermediate aquifer. Below that, we have the Thanet sand, typically 12 meters thick. And this is a uniform, dense, fine sand, and it forms part of the lower aquifer. It fines downwards. And below that, we have the chalk. Chalk is a very pure white limestone, well known from the White Cliffs of Dover, where it outcrops. It's typically 200 meters thick, although we tend to consider that only the top 50 meters is water bearing. And the permeability is derived essentially from the fractures in the rock. The fractures, it's pretty anisotropic as well. We'll look at that again in a bit more detail. So if we look at the hydrogeology, here I've got a plot of pore pressure against depth. We tend to use two datums here. So one is tunnel datum, which is what this is, where 100 is sea level, or we use ordnance datum, where 0 is sea level. So in this case, 100 is sea level. On the right, you can see the geological sequence that we've just talked about, which identifies the three aquifers, upper, intermediate, and lower. And we've got a series of dots on there. They're actual pore pressure measurements from piezometers. And these essentially in around about the City of London and central London. It seems likely that prior to about 1830, the pore pressure profile was hydrostatic from just above sea level. What happened was in around about 1830, people worked out how to drill through the London clay and tap into the fresh water in the lower aquifer, and wells proliferated in central London. Because the recharge is relatively remote, the water level was drawn down and we get this underdrained profile. Pumping actually started reducing from about 1950, and there's been a bit of a rise in water level, but that's now managed in order to maintain the infrastructure dry, because that was all constructed on the basis that the water level would remain low. So we finish up with this sort of sawtooth arrangement, and we're essentially looking at the intermediate aquifer, which is hydrostatic here, and then the lower aquifer. This actually varies. In central London, it's substantially underdrained. As you move out from the centre, the amount of drawdown from this historic pumping reduces. This is the graph. It's in the Syria guide. It shows it shows the different methods of dewatering: well points, deep wells, ejector wells, and it's a graph which plots the two key parameters that control selection of method, and those parameters are the drawdown on the left-hand scale. I've got going 0 to 20 meters, and the permeability from 10 to the -8, a virtually impermeable clay, up to 10 to the -1, more or less infinitely permeable gravel. And what we can do is we can plot on here the actual permeability ranges for the various strata that we have in London. So the terrace gravels at the top, relatively shallow, good for well point dewatering. Then we have the Lambeth group below. That's mostly clay, but it does have these sand horizons where the permeability is up to 10 to the -5. So that's sort of ejecta territory. Thanet sand, there's uniform fine sand, and then below that the chalk, which has a permeability that tends to reduce with depth. So one of the reasons why London is an interesting area to learn about dewatering is because of the wide range of permeability conditions that we have. The other key thing we have to think about is the boundary conditions. The Lambeth group channel sands and the Thanet sands actually have very similar geotechnical properties to the soils that I've spent some time looking at in Toronto along Eglinton Avenue, in that they're both dense, medium to low permeability, fine sands with varying silt and clay content with cohesive layers. What's different between London and the soils in Toronto is the boundary conditions. So the Lambeth group, the intermediate aquifer, is relatively low transmissivity. It's got barrier boundaries above and below due to the clay, and the lateral recharge is limited and distant. And that means we get potentially large distances of influences and relatively low flows. The Thanet sand, which forms part of the lower aquifer, is low transmissivity. It has a barrier boundary above, formed by the clay in the Lambeth group, but it has a recharge boundary below from the chalk. And the recharge is significant and it's very close. So we get very rapid recovery if we pump directly from the Thanet sands. So we have a limited distance of influence. The flow and the well yields are limited by the low permeability of the sand. And then below that, we have the chalk. This is a major water supply aquifer. It has a medium to high transmissivity. It underdrains the Thanet sand when it's pumped. It generally has limited recharge from below, but occasionally you do have subvertical fissures, and we'll look at that in one of the case studies. And the lateral recharge is very distant, just to the north and south of London. So we have very large distance of influences, potentially high flows from the chalk, and potentially high well yields. So it's these boundary conditions actually that we spend a lot of time looking at and trying to exploit. We also have to consider the structure and the physical and regulatory constraints. Does the side face support provide any cutoff? If it's diaphragm wall or a secant pile, grouting, it perhaps does. Contiguous piles, sprayed concrete lining, no. What is the required drawdown? Which aquifers do we need to be focused on to provide stability? What are the constraints in terms of access due to buildings, roads, railways, canals, rivers? Who owns the land at the surface? And below ground, there's a multitude of different tunnels that we have to check to see if we have full access. We also have regulatory constraints which evolve over time. A lot of those are around protecting existing abstractors from the chalk because it is a public water supply. There's potentially legacy contamination. And we have constraints on discharge. Discharge to the Thames if you can get access to it, but discharge to sewer, the capacity is strictly limited. This is actually an artwork by the artist Stephen Waller. It's a map of London, but it has marked on it just things which are under London. So it includes the river, so you can see where we are. But all the other lines on there are actually tunnels, basements, sewers, pedestrian tunnels, water mains, power tunnels, government tunnels from the Second World War, a whole variety of this, including quite a lot of redundant tunnels now. My experience is summarized there on the left, and I've just marked up the location of the case studies that we're now going to move on to. Note that there's a little bit of an eastward bias because the clay thins effectively as we go east. We're actually going to look at 6 case studies, there are 2 of them at the Limo site. So the first case studies is a couple of them. These essentially in the clay and in the Lambeth group. The first one is just very short. It's just a single slide. And it's the auxiliary shaft at Limo for Crossrail. It's a 27-meter diameter shaft. It's 40 meters deep. And the shaft was constructed in the London clay. But the base of the shaft finished about 5 meters above some sand channels in the Lambeth group. And these had an excess head of about 30 meters. So the solution here was relatively straightforward. We simply installed 9 passive relief wells. So these are just wells drilled within the footprint of the shaft. And once excavation extends below the standing groundwater level, those begin to flow. The flows were relatively low, just a couple of liters per second from all 9 of them, and that could relatively easily be managed by sump pumping. So that's a relatively low-cost solution to solving what is potentially a major problem. If you excavated without the pressure relief, you would dig in the dry until the excess head exceeded the weight of the plug, and you would have then had a blow in the base. So it avoided that. So that's a simple, straightforward solution for the shallowest project we're looking at. The next case study is again part of Crossrail. It's a cross passage CP6. So the running tunnels were driven by TBM. They didn't need any groundwater control, but there was a series of cross passages linking the 2 tunnels. These were for safety and to deal with leakage flow. This particular cross passage had a sump in the middle. You can see on the section there. The nearest borehole, it was just 10 meters away, showed that the tunnel horizon was predominantly in clay. They were the thin sandy clay horizon that I marked there, but that didn't seem too much of a concern. But we did know that there was a risk of channel sands because we were in the Lambeth group. And the sump reaches down into the standing groundwater level in the Lower Aquifer. So we knew we had an issue to deal with in the sump. This is what the construction looked like. So the construction is with SGI rings. Is actually a conventional timber heading between the 2 running tunnels. Once it's complete, then there's a shaft sunk in the middle down to about 5.5 meters. So the sump was just out of reach of a single stage of well points. Simply too deep. The well points would need to be installed from the or the wells would need to be installed from the TBM tunnels. Wasn't room in the cross passage to get wells in there. And if we hit any sand layers in the Lambeth group, then the intention was to tackle those with well points because we would be at a significantly shallower level. So that's what the plan looked like in section. We had deep ejectors installed targeting the lower aquifer to take the pressure off the sump. And then we had a series of holes which were essentially probe holes to prove that the expected ground conditions were clay and that the tunnel could be, the cross passage could be constructed safely without encountering groundwater. So that's what the sump ejector system looked like. It was all drilled from one tunnel, and you can see drilled at a sort of variety of angles to try and get below and around the sump, which was about 7 or 8 meters away from the tunnel. And this was the setup for drilling the probe holes. The SGI rings that you can see there, that's the opening set for the cross passage. And we're having to drill upwards, so we have a drilling rig that has a bit of reach, can reach up, and the drill rig operators have got a man lift there to work from. You can see the lower, there's a well point just below the driller there. No water coming out of it. That was drilled in clay and finished with a well liner, but there was nothing coming out of it. As we're drilling this upward one, we're auger drilling, and surprise, we hit a sand horizon and we got water coming in, water and sand coming in. So we have to stop drilling, pull out, put a stuffing box onto the drill hole, and then drill using a lost bit technique to install a well point to target that sand layer. So that was the process that we were going through. Although the expectation we were going to be working in clay, we knew that there was a risk that we could encounter a sand channel. So all the procedures and equipment to deal with a sand channel were on hand, and we found ourselves having to use that. What we gradually worked out from the drilling and from careful logging was that the eastbound TBM drive to the left was largely in clay with a little bit of sand in the crown, and the westbound was pretty much in the middle of a sand channel that was quite thick and had plenty of water in it. So in plan, this is what we finished up doing. The sump ejectors are in blue, drilled from the eastbound tunnel. The downward probes are in green, upward probes in red, and then there are a number of locations that were not installed. And essentially we were just drilling and monitoring the pore pressures to check that they were coming down. And as we installed well points, we connected them and pumped on them. As the pressure came down, it then became easier to drill in subsequent well points. And what we established in the end was that we had a sand channel. The axis ran obliquely across the tunnels by that. And you can see there why it wasn't necessary to install some of the wells, because they were outside the sand channel. The sand channel tends to be coarser towards the middle, so target the well points towards the middle and you get the pressure down, and that proved effective. Okay, so that was a couple of case studies in the Lambeth group. We're now going to look at Thanet sand. We've actually got 3 case studies. We've got the limo drive shaft we've got the Tideway, Kirtland Street shaft, and we've got the Docklands Light Railway. So the first one we're going to look at is the Tideway, Kirtland Street shaft. So all the jurisdictions that I worked in the last 20 years have permissions and consents to carry out any dewatering. So you have controls on abstraction, you have controls on discharge. The focus tends to be on the need to protect existing users and the environment. This project has the reverse problem, where we found that the existing users were causing the project a major problem. So the Kirtland Street shaft is constructed on the banks of the River Thames, just to the south of the river there. The shaft itself was constructed with deep diaphragm walls and needed relatively minimal pumping from inside the shaft, was not a problem. The issue was the TBM launch adits. These were constructed using sprayed concrete lining techniques, and that required some pressure reduction in the Thanet sand. And just 70 meters away, there was a major public water supply well, which targeted the chalk aquifer, and that had a license flow of 80 litres per second and an operating flow of about 60 litres per second. I should just add that the colouring on that is the red colouring means it's a source protection zone 1. So this is an area where the because of the public water supply, we have sort of enhanced protection measures and we have to be careful about what we do. So there's the ground profile on the left, London Clay, the Lambeth Group and the Thanet Sands. The adits are actually in the Lambeth Group, but what we're talking about is the need to reduce the pressure in the Thanet Sands. And we had to reduce the pressure by around about 12 meters from 87 to 75 meters tunnel datum. The public water supply abstracted from the chalk. The water supply well actually hadn't been used for 3 years, but it was turned on just as we started the project. And once the water supply was turned on, it in fact achieved the drawdown that we needed for the project. The problem was that they didn't pump continuously. Every now and again, sometimes several times a day, pumping stopped. And when the pumping stopped, the water levels recovered almost instantaneously. What we had to set up was a system that monitored a piezometer at the site boundary, which was that the grey line there. And as soon as we saw a rise in the water level there, that triggered our pumping system to turn on. It was on a variable speed drive, so it would ramp up pretty quickly because the pumps was mostly running on tick over. And you can see on the along the bottom there, the blue, that's the flow rate that we're pumping. So a lot of the time we're pumping almost nothing, but every now and again we're having to jump up to about 40 litres per second and occasionally even more. You can also see this period. This was when the pump in the water supply well failed on Christmas Eve, and it took them until March to replace it. So our system for that period was having to run pretty much continuously. So here we had the reverse problem. We were essentially having to manage the fact that an existing user, protected user, pumped the water at a variable rate. And we had to set our system up. We couldn't set our system up to pump continuously because that would have robbed water from the water supply well. So that wasn't acceptable. Okay, next case study is the drive shaft at Limo. So on the right, you can see the shallow passive relief, shallow shaft where we use passive relief wells. And to the left is the main drive shaft, which has a diaphragm wall around it. You can just see the sheet piles and the sprayed concrete lining for the auxiliary shaft. So the drive shaft was 30 meters diameter, 44 meters deep, had a 55 meter deep diaphragm wall. The TBM drives came from here, and also it was going to become a ventilation shaft in the permanent condition. So this is the profile, but we're sufficiently far east that we've actually got pretty much almost hydrostatic conditions from a high level. So we're out of the influence of that under drainage. And we've got the river gravels, channel sands, the Thanet sand, and the chalk. So the construction, first of all, diaphragm wall went down. I'm only showing half the shaft here, just for clarity. That cut off the river terrace gravels. The shaft was then excavated to full depth, which is right on top of the channel sands. This was when we need the maximum dewatering. We needed substantial pressure relief in the Thanet sand, and obviously we needed the channel sands to be dewatered, although they're in fact cut off by the diaphragm wall. Then the base of the shaft is installed. The TBM tunnel is driven. And this is quite a lengthy period, so we wanted to minimize the amount of pumping during this period. Once the TBM drives are finished, the shaft base is finished, the lid is put on, and then no dewatering is required. Pumping tests were undertaken in each horizon, and in order to achieve the dewatering for that worst case, when the excavation is to full depth without the base slab installed, we had 7 chalk wells on the outside, 6 external Thanet wells, 6 internal Thanet wells, and also 3 Lambeth group wells, which just operated passively. So a lot of the reason for this arrangement, so the chalk wells were achieving, we didn't actually need any drawdown in the chalk wells, but by pumping from the chalk, we underdrained the Thanet sand, and that significantly reduced the number of wells we would have needed in the Thanet sand. In plan, this is what the array looked like. The chalk wells have a big distance of influence, so they don't need to be close to the shaft. They can be some distance away. If you put them too close, they interact with one another and you don't get the yields. The Thanet wells have a very local impact, so they needed to be very close to the shaft. We had some on the inside and some on the outside, and we'll see why in a minute. And the Lambeth group wells are there on the inside of the drive shaft, and you can see one's on the inside of the auxiliary shaft. And we had a big array of piezometers in all the different strata, so we can see what was going on. Once the main shaft, once the shaft base was constructed, we were able to reduce the pumping, and we were actually able to turn off the chalk pumping completely and turn off the external Thanet wells, and we simply had passive relief inside. And that was sufficient for the whole period that the TBM drives were taking place. So essentially we were using the wells to target each horizon that needed dewatering, and simply just dewater it enough to get the shaft down. So this is what the data look like. We've got water level on the left, Kime along the top, we've got just over a year covered. This was the period when the shaft was excavated and the base, the initial base cast, and the flow on the right. So to begin with, for the first few months, we're only pumping from the chalk. And you can see the flows are quite high, jumping up to 160 litres per second. And the thanate sand and the chalk drain together. That's the red and the green lines. And we're getting about 18, 19 meters of drawdown. Then in March, the thanate wells pumping commences, and you can see we then we get the thanate flow, which is just a fraction of that. It's just 10 litres per second, but we get an extra 10 meters of drawdown in the thanate, and that's the target drawdown that we needed to get the shaft base in. Once the shaft base was in, the chalk flow was turned off. The chalk well, the green, recovers pretty much back up to the original level. But we've then got the passive relief wells from the thanate, and that's giving us the sort of 12 to 14 meters of drawdown to minus 20 that we need just to maintain stability while the TBM drive is complete before the full shaft is finished. So that essentially saved us pumping from the chalk at those high flows for the 2-year duration of the TBM drives. Okay, next case study. We're now looking at the Docklands Light Railway extension to Greenwich, and we're looking at the construction of a cross passage. So it was twin tunnels under the Thames. There's just one tunnel shown here, twin TBM driven tunnels. And there was a single cross passage at the deep point underneath the middle of the river. And that was at 27 meters below high tide. The original intention was to construct this using compressed air. So there was a bulkhead put in, one bulkhead down near the cross passage, a second bulkhead quite a long way away up where the ground was relatively shallow. They actually needed 3 bar of compressed air pressure to counteract the water pressure at the tunnel. They pressurized the tunnel. This was a trial pressurization up to 3 bar. And there must have been an air leak at the shallow level. And the air leak led to instability in the tunnel. And they actually blew the top off the tunnel on the north bank there. And the tunnel promptly flooded. The other tunnel was unflooded, and the project really was how do you move forward from that position. So in plan, we've got the River Thames, Isle of Dogs to the north, Greenwich to the south, just off Greenwich Pier. We've got the 2 new tunnels installed. There's the blowout you can see on the north bank and the proposed cross passage underneath the middle of the Thames. There was a recovery cofferdam to repair the damaged tunnel. That used, the damaged tunnel was in the Lambeth group, so that used ejector wells, and that was effective. But the cross passage looked like this. It was constructed in the middle of the Thanet Sands. One tunnel was now flooded. We're directly under the river. We got about a 5 meter tidal variation. Prior to the blowout, the project was 3 months ahead of program. The cross passage was the last item to be constructed before handing over the tunnel to the M&E contractor. The main contractor was reluctant to proceed with compressed air at 3 bar. He wanted to do it another way. Freezing probably would have been the obvious way forward, but that required access to both tunnels and meant there would be a minimum 6-month delay. So they wanted a solution that would allow them to construct the cross passage from the dry tunnel whilst they sorted out the wet one. So the proposal that was developed was to install 8 wells in the river from a jack-up barge, and these were to target the chalk. So the river wells were installed from a jack-up barge. Generators were on the barge, power cables running underwater, divers needed to put the pumps in. We actually split the power supply. We had generators on shore and generators on the barge. Then we also had some in-tunnel well points to get a bit of extra air down. And we had provision for compressed air, mainly for the sump, but at less than 1 bar, which was relatively straightforward. So those are the in-tunnel well points. This is back in 1998, so we haven't quite got the same health and safety arrangements that we have now. But these well points were getting a pretty good yield from the Thanet sand when they were installed. And these are the pumps being installed by the divers from the crane barge. And the pumps, we had a hanger, a valve, a flow meter. We needed to be able to monitor what was going on the discharge, the head plate that was bolted to the top of the wells, and then the pump riser, which was a flexible riser arrangement. We could only put the pumps in at slack water. When the tide was running, we couldn't put the pumps in, so we only had an hour either side of slack water to get the pumps in. That's the jack-up barge just off Greenwich Pier in middle of the summer, installing one of the wells. So we had the river above. That obviously wasn't a boundary condition because we had a clay layer that was protecting us. We under-drained the Thanet sand by pumping from the chalk. The combined approach of the surface wells, the in-tunnel well points, and the compressed air gave us a lot of flexibility. This was sort of early days of automated remote monitoring, which was essential because of the rapid recovery if the river system wells stopped. So we needed to be able to alert people in the tunnel almost immediately. We had interesting program constraints caused both by the tide and the Soccer World Cup, because none of the divers would turn up if England were playing. Fortunately, they got knocked out fairly quickly. And the dewatering system was actually installed and the cross passage completed in 3 months. So it was a great collaborative project. So our final case study is a case study in the chalk. This is another of the tideway shafts to the east, Deptford Church Street. And I'm indebted to Tideway Project and Costain Vinci Bashi joint venture for permission to use this case study on what is in fact an ongoing project. So the tideway sewers are a solution to a problem that we have in London, that we have a combined sewer system with the foul and the surface water sewer, both discharging into the same pipes. That was a Victorian system. As a result, when it rains, it tends to overflow into the Thames. So this is a new tank sewer. It picks up the existing outfalls and instead of overflowing to the Thames, it drops into the tank sewer, and that attenuates it and allows it to be pumped through the treatment works. So this particular shaft is 18 meters diameter, it's 60 meters deep, with diaphragm walls around it, and then it has a shallow interception chamber, which also in fact needed dewatering, but we're not going to be looking at that. So in section, we've got our shaft. The shaft depth is 50 meters. You can see that a lot of the superficial soils aren't present here. So we've got the river terrace deposit straight over the Thanet sand and the chalk. So the shaft is going well into the chalk. And what the hope was is that the diaphragm walls would reach to sufficient depth that inflow into the base of the shaft would be nominal and could be controlled by sump pumping. In order to check this out, the strategy is to install a chalk well. Chalk well is typically drilled with a steel casing, which is back grouted into the top of the chalk, and then we actually open hole in the chalk. It's sufficiently stable for that. And then we carry out geophysics and a pumping test. We use that information to review the depth that the diaphragm wall is going and to provide advice on grouting and possible grouting options if we think that's needed. Then they install the diaphragm wall. Then we actually install a second well and we repeat the pumping test to confirm that the diaphragm wall is doing what it's supposed to do before they excavate. And the contingency methods were extending the diaphragm wall, extending a grout curtain below the diaphragm wall, or base grouting. But base grouting had uplift issues and also significant expense. One of the things we do with chalk wells is we often develop them using hydrochloric acid, typically 1 or 2 tons. This is a strategy developed by the water supply industry and essentially adopted by dewatering. The acid dissolves the drilling slurry and generates large volumes of carbon dioxide. So it's essentially explosive, which is why those people are dressed up in suits. And you can see the wellhead there with the pressure gauge. As the gas is generated, pressure is generated, we monitor the pressure and bleed off the carbon dioxide. After the acidization, we have clearance pumping to clean out the well before we put it into production. So that's the well installed on the left. That's the open hole section in the chalk. And this is some of the geophysics that we run. So we typically run a caliper log. It's open hole. So at the top, you can see it's a little bit at the top there, you can see it's dead straight. And then you get the wiggly line, which may pick up some of the fissures. We run conductivity logs, temperature logs of the water. But the key thing we look at is the uphole velocity. So what we do is we actually install a pump in the well with a flow meter below the pump, and we can lower the flow meter down the well, and we can measure the uphole velocity as the water is being pumped. Obviously at the bottom of the well, the uphole velocity is 0, and as we come up the well, we expect flow to be entering the well and flowing up to the pump, which is up at a high level within the casing. And I've marked on there the dig level, just over 52 meters depth, and the toe of the diaphragm wall, which was at about 62 meters below ground level. So what the fluid log indicates is that virtually all the water is entering the well at 66 meters below ground level, and that was 4 meters below the proposed toe of the diaphragm wall. So the obvious suggestion was, why not deepen the diaphragm wall by 5 or 6 meters so that that horizon is cut off? The catch was that we also had optical image log, and what that showed is the inflow was from an inclined fissure, dipped 70 degrees north, very steeply inclined, and that means although it was cut off on one side, on the other side it would pass 40 meters below the diaphragm wall. And from the pumping test, we estimated that the inflow from that fissure could be in excess of 100 liters per second, which is way too large to discharge. Significant cost and program implications, and we needed additional site investigation. So that's what we projected. That is the shaft and the projected angle of the fissure cutting through the shaft. We actually drilled 2 further wells, one up dip and one down dip, and these are the fluid logs and the optical logs from those, and they show a virtually identical feature, almost exactly where it was predicted to be. And you can see in the bottom one, 80 meters below ground level, way below the depth of the diaphragm wall. So there was a lot of head scratching about what to do. They really didn't want to do base grouting because of the delay implied by that. So they actually took the opportunity to inject the rock mass via the 3 wells that were installed in the shaft. These were the results of the grouting. They estimated the volume of the fissure was in the shaft, if it was 2 inches wide, was about 50 cubic meters. They actually pumped grout into the wells, and by looking at the net volume of grout that went beyond the went out of the wells, they estimated that they grouted about 38% of the fissure within the footprint of the shaft. This is actually a photograph of the grouted fissure exposed in the base of the shaft. So the grouting was undertaken using the 3 initial test wells. Another 2 relief wells were installed and tested, and those showed that actually the inflows were now minimal as a result of that grouting activity, and the shaft was then successfully excavated with inflow of just 2 liters per second. So this was a very good result to a potentially challenging problem, resolved largely using a panel of experts who reviewed the information and developed the next steps in the strategy, and we successfully avoided the need for base grouting. So that is the end of my presentation. That last photograph shows a shaft on the London 2012 cable tunnels. In this shaft, actually, the Lambeth group is dewatered with ejector wells, the chalk dewatered with deep wells, and you can see 2 stages of well points in the bottom there, controlling residual seepage in the Thanet sand. That's the first time we've used all of our standard methods on a single shaft. And on the left there is what I've covered through. Thank you very much.